You are standing in a dark control room while a speaker releases a faint, grainy tone from beyond every planet you know. Voyager 1 is a small, old machine, easy to overlook beside rockets, rovers, and giant telescopes. What it sends now may decide whether the edge of our solar system is a border, a wake, or something stranger, and that turns the whole story ahead. Stay close through this one, and you will hear why a dying signal can still redraw the map around Earth. There is no fire in that room. No countdown, no cheering, no bright screen full of new worlds. Just engineers waiting almost a full day for a reply from a craft launched before many parents were born. When the answer comes, it arrives as numbers first, then meaning. That delay matters more than it sounds. A message leaves Earth, races outward at light speed, and still takes more than 23 hours to reach Voyager 1. The return trip takes another day. Every choice is made in the dark, with the past speaking back slowly. And that is why the idea of a last transmission feels so heavy. People imagine one final whisper, one sad farewell, one weak proof that the old probe is still alive. But the truth is more unsettling than that. Voyager's final era is not just about ending, it is about revealing where ending begins. Because the farther Voyager 1 goes, the less it behaves like a museum piece. It acts more like a weather station dropped into a sea no human being has ever touched. Its instruments do not send poetry, they send pressure, particles, magnetism, and the shape of a frontier we thought we understood. And lately, those stubborn bits of data have been telling a very different story. Not a clean line between the sun and the stars, not a simple crossing from inside to outside. What may become Voyager 1's last useful transmissions are showing us that the space beyond our system is still tangled with us. To see why this matters, we need to step back. Most people think Voyager 1 already did the important part years ago. It flew past Jupiter and Saturn, took the famous pictures, crossed out of the solar system, and now it mostly survives on nostalgia. What remains, people assume, is a long fade and not much else. That assumption feels reasonable. After all, this is a craft built in the 1970s, powered by plutonium, talking through a shrinking trickle of electricity. Its cameras shut down long ago, its parts are aging, its heaters are sacrificed one by one, and its voice reaches us from a distance so large it almost stops feeling real. Voyager 1 began as part of a grand chance in celestial timing. In 1977, the outer planets lined up in a way that let one spacecraft slingshot from world to world. NASA took the shot. Voyager 1 launched on September 5, 1977, 16 days after Voyager 2, but on the faster path. It was never supposed to be a 50-year witness. Its planned mission was short by today's standards. Fly past Jupiter, fly past Saturn, return what you can before the hardware gets old and the mission ends. Instead, the probe kept outrunning its own job description. It found a faint ring around Jupiter. It helped reveal violence in Jupiter's atmosphere and volcanic chaos on nearby moons. At Saturn, it discovered new moons and a new ring, and it saw Titan wrapped in a thick orange air that hid the surface below. Then it did something quieter, and maybe even greater. After Saturn, Voyager 1 turned upward and away from the flat plane of the planets. It left the stage where most space stories happen. No more close flybys, no new postcard worlds, just a long climb into colder and darker space. That is where public attention thinned out. A spacecraft with no fresh pictures is easy to forget. A probe measuring particles and fields sounds less exciting than one filming storms over Jupiter. Voyager became famous in memory, not in the daily present. People kept the golden record in mind more than the instruments still working. But inside mission rooms, it never became sentimental. It remained a machine with tasks. Its radioisotope power system, called an RTG, made electricity from the heat of decaying plutonium. At launch, each generator produced far more power than the craft would have later. Year by year, that output dropped, and the accountants of survival took over. Heaters were turned off. Systems judged non-essential were sacrificed. Cameras had already gone dark in 1990 after the family portrait and the pale blue dot image. Other instruments followed. By the 2000s and 2010s, Voyager 1 was living on disciplined subtraction, a little like a house during winter where only a few rooms stay warm. Yet even then, the mission refused to become just a sentimental relic. The Voyager interstellar mission officially began in 1990. The goal was now simple to say and hard to do. Keep going until the probe reaches the edge of the sun's domain. Cross it if possible, and listen to what lies beyond. That edge sounds like a hard shell, but it is not. The sun sends out a stream of charged particles called the solar wind. That wind inflates a vast bubble around the planets. We call the bubble the heliosphere, and it helps shield our neighborhood from some of the harsher radiation of the wider galaxy. Most people picture the heliosphere like a neat boundary around the solar system. Inside is us. Outside is the true interstellar medium, the thin gas and magnetic field between stars. Cross the border, and the story should become clean. New field, new particles, new chapter. Even scientists once hoped the crossing might look that clear. In 2013, Dr. Ed Stone of Caltech, Voyager's longtime project scientist, explained that the team expected a sharp change in magnetic field direction when Voyager entered interstellar space. That mattered because Voyager 1's own plasma instrument had stopped working back in 1980. So the mission needed other clues to tell inside from outside. That missing instrument shaped everything. Without direct plasma readings, the magnetic field became a stand-in, a proxy, a clue by behavior. If the field snapped into a different direction, then maybe the craft had crossed. If it did not, maybe it had not. That became the quiet rule in the background. Meanwhile, Voyager kept moving farther out. It passed 100 astronomical units in 2006. 1 astronomical unit is the average distance from Earth to the Sun. By then, Voyager 1 was far beyond Pluto's orbit, in a place where sunlight is so weak it would feel like a cold memory. Still, the craft kept reporting, and the reports were already strange. Years before the famous crossing announcement, Voyager had entered the heliosheath, the disturbed region near the edge of the heliosphere. There the solar wind had slowed, heated, and begun to feel the pressure of interstellar space. That was supposed to be messy, yes, but maybe not deeply surprising. Instead, surprise piled up. A 2005 science report described 3 shocks to expectation. The solar wind beyond the termination shock slowed far more than expected, and at times even seemed to flow back inward. The magnetic field changed direction much more slowly than predicted, and the cosmic rays that should have peaked at the shock kept growing stronger farther beyond it. That should have been a warning. The edge was not going to behave like a textbook line. It was going to act like surf, pressure, traffic, and weather all at once. But from a distance, it was easy to keep the old picture. Voyager was old, the border was simple, and one day the last signal would mostly confirm a graceful decline. Even the scale helps people underestimate it. Voyager 1 is not the size of a battleship. It is about the size of a small car, with a dish antenna and long booms extending outward. Its instruments are modest by modern standards. Its memory is tiny compared with the phone in your pocket, and yet this small thing became the first object made by human hands to reach interstellar space. Not because it was flashy, because it endured, because each spare watt was argued over, each heater reconsidered, each thruster branch used like an old tendon still doing its job after decades. By the early 2000s, the prevailing story felt settled. Voyager was nearing the boundary. The craft would either cross and tell us in some simple way, or it would fade before we learned much more. Most people, and even some casual space fans, took for granted that whatever came next would be symbolic first and scientific second. That is the picture we need to hold for one moment longer. A historic but fading probe, a border that should reveal itself clearly. A final transmission that would matter emotionally more than intellectually. That whole picture is about to crack. What we have just taken for granted turns out to be a small part of a much larger story. Voyager 1 was not drifting into empty silence. It was drifting into a place so active, so structured, and so connected to the Sun that the old inside-outside story could not survive intact. Write the moment your own assumption shifted in the comments. That helps shape what this channel digs into next, because your turning point reveals where the real mystery begins. The first big break came in August 2012. Voyager 1 saw lower energy particles from inside the heliosphere fall away fast. At the same time, higher energy particles from outside surged upward. Expected story: magnetic direction changes, border confirmed. Actual story: particle behavior screamed crossing, but the magnetic field refused to make the dramatic turn. That left the team in a strange place. The craft looked outside by one test and inside by another. It was like stepping at your front door, feeling rain on your face, and then seeing your doormat still somehow dry. Ed Stone later described how that missing change in field direction kept scientists cautious. They had evidence, but not the clean evidence they expected. Then chance intervened. Months earlier, in March 2012, the Sun had thrown out a burst of material. That burst moved outward through the solar system and, 13 months later, reached the region where Voyager 1 was traveling. When it passed, it made the local plasma vibrate. Voyager's plasma wave instrument could hear those vibrations like tones. Those tones changed everything. They told scientists the electron density around Voyager 1 was more than 40 times greater than the plasma density in the outer heliosphere measured by Voyager 2. That density fit interstellar space, not the solar bubble. Expected story: the field would tell the truth. Actual story: sound like plasma vibrations told the truth first. In September 2013, the mission announced the conclusion. Voyager 1 had entered interstellar space on August 25, 2012. Not because a gate opened, not because the magnetic field gave a clean salute, because the particles changed, the plasma rang, and the density rose to a level that did not belong to the sun's inner bubble. Even there, the surprise kept growing. You might think interstellar space just outside the heliosphere would be calm, almost empty, a cold, still pond after the rougher edge. But in 2021, Stella Acker of Cornell University and her co-authors, writing in Nature Astronomy, described something more alive. Voyager 1 was hearing weak, persistent plasma wave emissions from mid-2017 onward. Expected story: only rare big shocks would let scientists map density out there. Actual story: a nearly continuous faint tone could track changes in density over long stretches of space. The comparison is almost eerie. It was like finding a dim note humming in an empty hallway and realizing the whole building has been speaking softly for years. Acker's work mattered because it turned sparse snapshots into a running record. Earlier, the dramatic whistles from solar eruptions appeared only now and then. Useful, yes, but scattered. With the persistent tone, researchers could follow density more regularly. That made the local interstellar medium look less like a blank void and more like a textured environment with structure. And the structure did not fit an easy exit story. Using those signals, scientists found the density around Voyager 1 rising after the crossing and then reaching high levels by around mid-2015. Instead of slipping quickly into a pure, untouched outside, Voyager seemed to be moving through a region still shaped by the heliosphere. Expected story: clean departure. Actual story: long, messy after effects. That idea linked back to an older puzzle. Years earlier, NASA and JPL had highlighted how the magnetic field outside the heliopause looked oddly aligned with the field just inside it. That was not what many scientists expected. If you cross from one domain into another, you expect a visible bend. Instead, the field looked more like a stretched line sliding around a rounded obstacle. Nathan Schwadron of the University of New Hampshire tackled that mystery in a study described by JPL in Astrophysical Journal Letters. His team argued that Voyager 1 was still in a distorted region where the nearby heliopause was deflecting the interstellar magnetic field. Expected story: outside means pristine. Actual story: outside might still carry the shape of the boundary beside it. His image was simple and useful. Think of a rubber band stretched around a beach ball. The field does not ignore the ball, it bends around it. That meant Voyager 1, though beyond the heliosphere, was not yet in some perfect, untouched sea. It was still moving through water folded by the wake of the sun's great bubble. Soon after that, the mission delivered another lesson, this time about time itself. The sun does not stop mattering the moment you cross the heliopause. Solar eruptions, pressure fronts, and the 11-year solar cycle keep sending disturbances outward. At these distances, they travel slowly, then hit the boundary, and then reshape the space beyond it. The border behaves less like a fence and more like surf. That brings us to one of the freshest and most important clues. In 2026, Federico Fraternale and colleagues described, in an accepted astrophysical journal study first shared on Archive, how Voyager 1 had seen a jump in magnetic field strength in 2020.4 at 149.3 astronomical units from the Sun. After that jump came a hump, and then persistently strong magnetic field readings. Expected story: interstellar space should settle down as distance grows. Actual story: the field stayed strong because solar cycle-driven compressions were still shaping it. That is a deep shift in meaning. It says the sun's influence does not end like a snapped wire. It fades, bends, and sends delayed effects into the very local interstellar medium. In plain words, the space outside our solar shield is still being sculpted by forces that began back home years earlier. Voyager is not just outside the house, it is still hearing the house creak. The 2026 modeling went further. It suggested those puzzling magnetic structures near Voyager 1 could happen once per solar cycle. It also predicted that Voyager 1 may keep seeing relatively strong magnetic field conditions until around 2030. That means some of the probe's last scientifically useful transmissions may come from a region that is neither simple wake nor pure open sea. It is a transition zone with memory, and memory is exactly what makes these transmissions so precious. Each data point arrives delayed by almost a day. Each one comes from hardware old enough to have been written off many times. Each one samples a place no other craft has ever reached. When a number changes there, it is not just a reading. It is a report from the farthest outpost humanity has ever built. The engineering story only sharpens that point. After decades in flight, Voyager's thrusters do not behave like fresh parts. Tiny fuel tubes have been slowly clogging with silicon dioxide, a residue that builds over age. A tube opening once about 1/4 of a millimeter across has narrowed to roughly 0.035 millimeters. That is about half the width of a human hair. In 2024, NASA reported a careful thruster swap to keep Voyager 1 pointed at Earth. The craft fires short puffs of hydrazine to tilt its antenna and stay locked on home. Expected story: old spacecraft drift and die. Actual story: engineers briefly turned off a main heater, warmed a colder thruster branch, and kept the ancient probe talking. Then, in 2025, came something that sounds almost impossible. Kareem Badarudin, Voyager mission manager at JPL, and the team revived a set of roll thrusters on Voyager 1 that had been considered unusable since 2004. They needed the backup before Deep Space Station 43 in Canberra, the only dish powerful enough to command Voyager, went offline for upgrades. Expected story: dead parts stay dead. Actual story: a suspected flipped circuit state may have been corrected from 15 billion miles away. Todd Barber, the propulsion lead at JPL, called it yet another miracle save for Voyager. That phrase matters because it shows how thin the margins have become. This is no longer a mission with comfortable backups. It is a mission of clever risks, patient waiting, and decisions made knowing the answer arrives the next day. The last transmission is not a theatrical moment. It is a possibility standing beside every command. And still, the science keeps getting richer. A 2024 paper led by William Kurth reported that Voyager 1's measured electron density remained around 0.147 particles per cubic centimeter through the most recent observations they analyzed from 2023. Expected story: once outside, density should simply settle into some final ordinary value. Actual story: the data suggested a broad plateau or peak, hinting at structure still not fully explained. Here is the important hesitation, because the story should not sound too neat. Scientists do not fully agree on every interpretation. They do not yet know exactly how much of what Voyager sees belongs to the pristine interstellar medium, and how much belongs to a disturbed zone shaped by the heliopause, solar cycle compressions, shocks, and turbulence. That uncertainty is not weakness. It is the clearest sign that Voyager is still finding the edge more complicated than theory once expected. Fraternal's 2026 analysis even notes changing turbulence behavior at different timescales. Some intermittency, meaning bursts of irregular change, seems to weaken after 2022. But the authors argue that may reflect weaker turbulence, not a total shift in the nature of the local interstellar medium. Expected story: farther means simpler. Actual story: farther can mean subtler, and subtle does not mean settled. So when people say Voyager 1 already finished the important part, they miss the larger timeline. The Jupiter and Saturn flybys made it famous. Crossing the heliopause made it historic. But these late transmissions are turning it into something rarer. They are forcing us to redraw the edge of the sun's influence, not as a clean shell, but as a living borderland. And that changes what last transmission really means. It may not be the last hello from an old machine. It may be the last sample from a once-in-history instrument passing through a once-in-history region. The end of the spacecraft and the birth of a new map are happening together. That is why the signal matters more now than ever before. If the reveal in this story is right, then the way we think about the subject will quietly shift for anyone who ever looks up. This stops being only about one probe and starts becoming a question about how we understand protection, distance, and home. Share this video with one older skeptic who thinks Voyager is just a retired relic. That is the right next step because this story lands hardest when someone discovers the future can still arrive through a machine from 1977. The wider human question is simple and huge at the same time. Where does a home end? If the sun's protective bubble leaves a long wake beyond its own border, then our place in the galaxy is not a neat room with a hard door. It is more like a campfire whose heat still reaches into the dark after the flames seem far behind. That matters for science, but it also matters for us. The heliosphere helps blunt some of the harsh, charged particles moving through interstellar space, so learning its shape, thickness, and behavior is not abstract trivia. It is part of learning how our planetary neighborhood survives in a rougher galaxy. Voyager is telling us how the shield around our broader home really behaves. The practical changes begin with models. If the region beyond the heliopause stays disturbed for years and across great distance, then future simulations of the heliosphere must include delayed solar cycle effects, compressions, and magnetic bending more carefully. That affects how scientists think about cosmic rays, boundary motion, and what a future interstellar probe should expect when it leaves. The old clean border picture is no longer enough. It also changes how mission planners think about timing. A probe sent outward does not simply pass from one environment into another. It may cross into a zone where the sun still speaks, just late and distorted. That matters for instrument design. It matters for how often data must be sampled. It matters for what counts as true interstellar baseline conditions. The timing of Voyager's own survival has suddenly become part of the science case. On April 17, 2026, NASA shut down the low-energy charged particles experiment on Voyager 1 to save power. Kareem Badarudin said the craft still had two science instruments operating well, the plasma wave subsystem and the magnetometer. Those two tools are exactly the ones best suited to reading this borderland in late life, and the power math is brutal. Both Voyagers lose about 4 watts each year as their radioisotope systems weaken. That is less a dramatic collapse than a steady tightening. A lamp dims, a heater goes silent, an instrument waits its turn. The mission survives by shaving fractions from a half-century-old machine without letting its fuel lines freeze. Linda Spilker of JPL has said the science data get more valuable the farther from the sun the probes go. That sentence is easy to miss, but it turns normal space logic upside down. Usually, older missions give less. Voyager can give more precisely because nobody else is there. Distance is not reducing value. Distance is creating it. That is why NASA's 2026 Big Bang power strategy matters so much. The idea is not explosive in the usual sense. It means swapping groups of powered devices at once, turning some off and replacing them with lower power options so the spacecraft can stay warm enough to keep gathering science. A desperate plan, yes. Also a rational one. Suzanne Dodd has said future decisions for Voyager will require far more analysis and caution than they once did. That caution is not just engineering wisdom. It is the price of operating a craft where one wrong move may cost the only measurements we have from that part of space. By July 2026, NASA planned to try the same broader energy-saving approach on Voyager 1 after testing it on Voyager 2. That tells you how close to the edge the mission now lives. Now bring that down to Earth for a second. You use GPS. You rely on satellites for weather, timing, communication, banking, and maps. You may notice auroras when the sun grows active, or watch news about solar storms and wonder why they matter. Voyager's work sits far beyond all that, but it teaches the larger truth behind it. Our star does not stop shaping our lives at Earth's orbit. The sun builds a giant magnetic and particle bubble around all the planets. That bubble is part shield, part moving frontier. Knowing how it bends and leaks helps scientists understand what radiation gets in, how cosmic rays are filtered, and how our local space climate works on the biggest scale. So when Voyager reports from the edge, it is not just talking about somewhere else. It is talking about the conditions that cradle us too. There is also a cultural change in this story. For years, interstellar space sounded like the after-credits scene of Voyager's life. Now it feels like the central chapter. The probe's old age is no longer just heroic. It is scientifically awkward in the best way. An old machine is finding that reality refuses to become simple just because the mission is nearing its end. Future missions will build on that lesson. The long-discussed interstellar probe concept, and even current outer solar system missions, will need to think about the heliopause not as a line to cross once, but as a region to study deeply. Fraternale's 2026 paper even predicts that New Horizons may reach the termination shock around 2031 at roughly 80 plus or minus 2 astronomical units. That means Voyager's story may become the training ground for the next generation. By late 2026, one number will hover over everything. On November 18, 2026, at 2:16:07 a.m. Pacific Time, Voyager 1 is expected to reach 1 light day from Earth. That means the spacecraft will be 16,094,799,096 miles away, or 25,902,068,356 kilometers. A command sent then will take a full 24 hours to arrive. A reply will take another full day to come back. Think about how strange that is. You ask a question on Monday and hear the answer on Wednesday. That is not conversation. That is archaeology in real time. And if the answer contains a tiny shift in magnetic strength or plasma tone, it may change how we define the outer skin of our solar home. By April 17, 2026, Voyager 1's active science list had already narrowed to the magnetometer and plasma wave subsystem. Those are not glamorous names, but they are perfectly matched to the question now unfolding. One reads the invisible pull and direction of space. The other listens to the faint ringing of particles. Together, they can still tell us whether the sun's influence has truly thinned or only changed form. And unresolved questions remain everywhere. How far must Voyager travel before the magnetic field looks fully pristine, if that word even makes sense here? Will the predicted strong field interval really last until around 2030? How much turbulence lies ahead? Could future power-saving moves buy enough time for one more crucial pattern, one more solar-driven compression, one more unmistakable clue? That is why the next transmissions matter so much, not because they will be emotional, though they will, because they may separate several competing pictures of the same region. A clean exit picture, a long, distorted wake picture, a layered story where both are partly true depending on scale, timing, and what the sun was doing years earlier. The beauty of Voyager 1 is that it does not care which story we prefer. It only sends what it finds: numbers, fields, densities, tones. No drama added. No effort to comfort us with simple borders. It has become the farthest honest witness we have, and honest witnesses often ruin tidy ideas. Something is coming next, even if it arrives slowly. Another delayed report. Another tiny shift in a magnetic field. Another faint note in plasma that tells us the dark beyond the planet still carries the afterlife of our star. Tomorrow, or next month, or next year, someone in a control room will decode one more fragment and realize the map needs moving again. What changes then is not only a chart in a paper, it is our sense of scale. A machine launched when disco was new is still teaching a digital civilization how a stellar bubble breathes. A probe older than most careers is still ahead of every newer spacecraft by an impossible margin, and the farther it goes, the less final the story feels. Soon enough, there will be a last, truly useful transmission. After that, power margins will close, heaters will fail, instruments will go silent, and the carrier tone itself may one day vanish into the background. But before silence wins, Voyager may still give us the cleanest clue yet about whether interstellar space near home is calm, compressed, bent, or all three at once. That is what makes this ending so alive. So save this video and come back when Voyager reaches 1 light day in November 2026. That private bookmark will give you a better sense of the scale, because the story will hit differently once a single message takes 2 days for a round trip. When that day comes, picture one small dish in the dark, one ancient machine still holding Earth in its aim. Picture the number instead: 24 hours out, 24 hours back. A full day for a human question to arrive, and a full day more for a machine older than the internet to answer. That is not the sound of yesterday hanging on. It is the sound of the future arriving very slowly. And when it does, I think it will keep telling the same quiet truth. The universe is not arranged in the clean lines we first draw for ourselves. Home is bigger, stranger, and more connected to the dark around it than we guessed. Voyager 1's last era of transmissions will not simply mark the end of a mission. It will help teach us what the edge of home was all along.